3. And then add a half rotation. So 2 pi over 3 plus n pi. Common denominators on those would give you pi over 3 plus 3 pi n over 3, which is pi plus 3 pi n over 3. Oh, wait, no, hold on. I can do it now. It's okay. I can divide by the 4. Hold on. But I don't want to do that. That's dangerous. Let me stop here. Hold on. Stop there. Let's divide the 4 now. We could get the common first and then divide by 4, but that's not the way I did it before. So from this right here, we divide both sides by 4. We get x is pi over 12 plus n pi over 4. And on this one, we get x is 2 pi over 12 plus n pi over 4. Let's get commons now. So I'd multiply the top and bottom of this by 3 to get a 12. So this should give me x is pi plus 3 pi n over 12. And then what about this one? What does that one become? 2 pi plus 3 pi n over 12. Those are my two sets of general solutions right there. Now, do you feel like if I gave you an interval now, you could go grab all the answers? Yeah? I'm not going to do it. This would take a while. If I gave you like from 0 to 2 pi or something, you would have a lot of answers in here. Okay. How are y'all feeling? Ready for the weekend? I'm willing to bet that I'm looking more forward to it than you are. All right, let's do this one. 2 sine squared 3 theta minus 3 sine 3 theta plus 1, let's make it minus 1, equals 0. Now this is different than what we've done before, because we have the trig function appearing twice. First it's being squared, and then it's by itself, not being squared. So if you squint your eyes, yeah, just go in there. Everywhere you see a sine 3 theta, everywhere you see that, replace it with a u. And if you did that, what would this look like? 2u squared minus 3u minus 1 equals 0. Isn't that what that would look like? And if you were looking at this quadratic equation, you were asked to solve it, you would factor that. And this is a quadratic trinomial. You would try and break it down in 2 parentheses like this, wouldn't you? What would those be if you did that? 2u here, u here.
Minus 2u, wait, minus u.
Minus, wait a minute, hold on. Yeah, let's do plus. Sorry, let's do plus. If I change that, I need to change the other one. So let's just turn that back to a plus. So what needs to go here? Minus 1 and minus 1. That's the way it would break down, right? And then you would just set each of those equal to 0, wouldn't you? You would be like, okay, 2u minus 1 equals 0. Then you would say, oh, u minus 1 equals 0. So you get a solution here, u is a half, and then here you would say u is 1, right? That's what you would do if this were the problem. And this is not the problem, but it's very similar to this, right? So I'm going to do the exact same thing. I'm going to break it down. This, I have to recognize this as being a quadratic trinomial, but it's what we call a quadratic, well, let me say it this way. This is what we call a quadratic in U. A quadratic in U, meaning that U is the variable. Here, this is a quadratic in sine of 3 theta. It's the U here is the part that's like the variable. That didn't make any sense. I'm just going to shut up. Let's just break this down. Sorry.
Sir, even if we solve it for u and we took u as sine.
Yeah, you just put sine theta here, we're done. Yeah. But I wanted you to see this first. If you need to make the substitution and do this, then do it. But I think as you move forward, you want to be able to do this without having to actually write this down. Like you want to see that in that without needing this on paper. So you need to be like, oh yeah, that's a quadratic. This is just going to be 2 sine theta minus 1, like that. So if you did FOIL on this, this times this would give you the first one. This times this would give you -2 of them. This times this would give you -1 of them, so you would have -3 of these things. And then -1 times -1 gives you +1. So I want you to see that, but with the first example, I wanted you to at least see this first. Yeah? Now you set each of those factors to 0. 2 sine theta minus 1 equals 0. The other one, sine theta minus 1 equals 0. And now you have 2 trig equations. These are 2 separate trig equations. You're going to do them individually and figure out what happens. So this one looks very much like one of the first problems we did. So I'm going to move the 1 over and divide by 2. Sine theta is 1/2. This one, sine theta is 1. Now you ready? Sine theta, that's the y-coordinate. Where's the y-coordinate? 1/2. Here, here. Where's that? Pi over 6, 5 pi over 6. They're not directly across from one another, so I need to include both of them in my general solutions. To get here back to itself, I have to go around by 2 pi. To get here back to itself, around by 2 pi. So I'm going to set the argument. Oh, crap, I forgot the 3 theta. 3 theta. Sorry, that's my fault. 3 theta. I didn't put the 3 thetas in here. Jeez, man. Y'all understand why those have to be there, right? The 3 thetas? That's the argument, right? I can't just all of a sudden change the argument from 3 theta to theta. All right, so here I'm going to say that the argument, 3 theta, must be equal to, let's do this one first. Pi over 6 plus 2 pi n. Now, I could get common denominator and create a list if I needed to from that, but that's one of them, and I need this one. So, or 3 theta equals 5 pi over 6 plus 2 pi n, right? Let's take care of this one while I'm over here working on this side of the board. What is this saying? Where is your y-coordinate? 1, right? It's here, and that's it. Just there and back to itself, Yes?
How come you went 2 pi instead of pi?
Ah, why did I do that? So if I was here, right, pi over 6 is here. If I add pi to it, right, just a single pi, that's going to take me directly across from it, which is over here, which is there, which is not part of our answers. I need to actually get all the way back to that same point. So I have to go by a full revolution. Same thing with this one. If I start at 5 pi over 6 and go by pi, I'm over here, and that's no good. I've got to go all the way around. If you look back on the previous examples, the reason why we added pi was because the 2 answers that we were working with were directly across from one another. All right, so here we need, what, 3 theta to be pi over 2 plus 2 pi n. Again, we have to go all the way around because we don't have an answer directly across from it. Now, I want to get my answers in terms of theta, not 3 theta. So I have 3 groups of answers here. Right? So the first one, theta is equal to pi over what? 18 plus 2 pi n over 3. So all I did was divided both sides by 3 here. Or we could have theta is 5 pi over 18 plus 2 pi n over 3. Or finally, theta is pi over 6 plus 2 pi n over 3. So I just took each of these, divided both sides by 3. Now I could get common denominators, right? If I wanted to. If I needed to create a list, I could. Do you all want me to get commons or just leave these and be happy and move on?
Yeah.
Yes? Be happy, move on? But just keep in mind, in the book, they are going to ask for the answers on an interval. So they're going to say, hey, give me all the answers between 0 and 2 pi. So then you have to put together, n equals 0, 1, 2, 3, 4, right? And it's going to take a little while. So what's over here would be referred to as the general solutions. Those are the general solutions. This will be our last one. Well, maybe not. Second to last one. How about this one? Cosine squared theta equals 2 minus sine theta. Solve this equation. How is this different than the ones we've done?
I got different variables involved.
Yeah, we've got sines and cosines mixed up here, don't we? The cosine is being squared, which makes it look somewhat quadratic. The sine is not squared, so I don't know. We can't just do a substitution right now and just be like, oh, replace sine with u, because then this is not sine, right?
Take that as 1 minus sine squared theta.
Okay, so we could use an identity now, right? We could take this right here and rewrite it as 1 minus sine squared theta. That's the Pythagorean identity, right? Now everything has sine in it. It's quadratic. Let's move everything over to one side. How about we go to the right side with everything? Is that okay with you? If I move this one over here and then the 1 over here. So I'd have a 0 on the left side. When my sine squared comes over here, it becomes positive, so I'm going to put it first. Then I'll have minus sine theta. And what about a number? What do I have?
Plus 1.
Plus 1, because I subtract 1 on both sides. Does that look like a quadratic to you? Yes? Does it factor? Doesn't factor. So this problem, this will be our last example, I believe. Yes, this will be our last example. This problem is presenting you with 2 new things to be aware of. You can use identities to get everything in terms of one trig function. And then even if you get it to a quadratic, now this new element is that it doesn't have to factor. Like there's nothing that says this has to factor. So if we try this, it's not happening, right? Y'all aren't able to come up with it? Yeah, cannot? Can, cannot? No? Yeah, you can try for a while. I don't think you're going to get anything. Now, maybe I'll do it one more time over here. Here's what we're trying to do. If we replace the sine theta with u, we have that, right? And we cannot factor in a way, the only way to get positive 1 here is to put 1 here, and make them both positive or both negative, right? And I can't do that because if I make them both negative, that's going to have to be negative 2. And if I make them both positive, that has to be positive 2. It's not happening. Does that mean there's no solutions? No. Just means I can't find them. What do we use to solve that if you can't factor? Quadratic formula, right? We use a quadratic formula. All right, so when we use the quadratic formula, remember, this is when we use a quadratic formula. When we have a quadratic that looks like this, the solutions are x equals negative b plus or minus the square root b squared minus 4ac over 2a, right? That formula that we all can say in our sleep, right? We've used that many times. It's been very useful. So what we do is we say, okay, if we have a quadratic in x, then the solutions to this equation are x equals this, right? And this is just the numbers, the coefficient here, coefficient here, coefficient here, just thrown into this weird formula, right? Here we have a quadratic in what? Sine theta. So if we use the quadratic formula, here's what it will supply us. It will tell us that sine theta, not x, sine theta is equal to negative b plus or minus square root b squared minus 4ac over 2a. All of that, right? So what is our a for this problem? What is a? A is 1, b is negative 1, and c is 1.
Like, probably, like, isn't it better if you like substitute them with a variable then solve them? Like, wouldn't it be more easier than using sine?
Is it better for you? It really just depends on you. I can tell you that, again, in my experience, the substitution part is there if it's helpful, great, but it's not something that you want to keep doing, like forever, to keep having to do the substitution. See, because this shows that you understand that the quadratic formula works with this. It's just not spitting, this doesn't spit out theta to you. It spits out whatever the variable is, in this case, sine theta, is what it's giving you the solutions as. And then look, once I have these answers, want to have sine theta equals two things? Because I'm going to have plus or minus. So I'm going to have two new equations with sine in it. I'm not discouraging you from using u. If you like u, then use it. I would just say try and wean yourself off of that at some point. All right. Negative b. What's negative b? 1. Plus or minus square root. What's b squared? 1 again. Minus 4 times a, which is 1, times c, which is, what is c? 1? All over 2 times 1. And what do we get here? Uh-oh. We got problems. Are we getting an imaginary number in here? Sine theta is 1 plus or minus the square root of negative 3, right? All over 2. And that's an imaginary number. And at that point, we put our weapons down and we concede. We say, we can't do this. Okay? So no real solution. Can't do it. Only because there's a negative root under here, all right? Well, that didn't work out the way I really wanted it to, but that's what the book showed you. Yeah, all right, so I'll have to supplement that with a little something here. We're done with this problem, okay? We're done? But I'd like to ask you, what would happen had we got something here that was crazy, but it was a real number? So in other words, what if I was sitting here with something like this? Sine theta equals 1 plus or minus the square root of, let's say it came out to be just the square root of 3 over 2 instead of negative under that root.
Then we do it in two parts. 1 plus root 3 over
Okay, so we would have two different things to look at here, right? We would have sine theta is 1 plus root 3 over 2. And then the other one would be sine theta is 1 minus root 3 over 2. This is asking you where on your unit circle is your y coordinate this. I don't know, I've never seen that on my unit circle. Have you? Okay, have you ever seen that on the unit circle? No, it's not one of the special angles. But let's get a calculator out and let's figure out where this is. Okay, so somebody that has their calculator, do 1 plus the square root of 3 and then divide it by 2. Anyone? Anyone? Any takers on that?
1.3660.
Say it again.
1.3666.
Okay, so sine theta is 1.366. Okay, can you do this one also?
Negative 0.366.
Negative 0.366. Thank you. All right. Now, what can you tell me about this? What's that? This is not going to have an answer. Why not? Why is there no solution here? It's not on the unit circle, right? We would ask ourselves, where on the unit circle is the y coordinate 1.3? But on the unit circle, your y coordinate, the biggest it can be is 1, right? So there's no solution here. No solution for this. What about that one, though? Yes, there is. Now, we're asking ourselves, where is the y coordinate what? Negative 0.366. That's going to happen. Well, here's negative 1, right? Here's negative 0.5, negative 0.366, somewhere around here. It happens here and it happens here. Do you all agree? Now, do we know what these angles are? They're not one of our common angles, right? They're not one of our common angles. This has a y coordinate of negative 0.366. This has a y coordinate of negative 0.366. You following me? Okay. Now, on your calculator, I would like for us to do this. If we want to know what theta is, we will take arc sine on both sides. So take arc sine of this side and arc sine of this side. And let's make sure that let's do it in degree mode, just so we can understand what's happening here. So someone on the calculator, make sure you're in degree mode and take arc sine of negative 0.366. What are you getting? Negative 21. Are you getting the same thing? Negative 21 degrees. So what that's telling us is that this angle right here is negative 21 point, was it point something? Point what? 0.4. So 0.5. Good enough? Degrees. Negative 21.5 degrees. Yes? Okay. What about this one right here? What's that angle then? It's 180 plus that angle right there, which should be the same as this angle, right? So shouldn't this be 180 plus 21.5? So that angle would be what? 201.5 degrees? Yeah? You'll see how I'm doing this? Okay. Now I'm staying away from radians. I'm doing degrees because degrees makes more sense visually to us right now. So from this right here, what could you tell me about theta? Theta would have to be this angle, which is negative 21.5 degrees, but you also need to be able to come back to this angle. How could you come back to this angle? You would add 2 pi, right? But we're in degrees right now. So you would have to say plus 360 degrees n. We've been using 2 pi n because we've been in radians. But if you're in degrees, it's full revolution times n. Do you see how this right here takes care of that answer and all of the answers? Am I done? No. Now I say, or theta is 201.5 degrees plus 360 degrees n. This is a little more complicated than what we've been doing because everything we've been doing, the angles have always landed in a nice place. They've always been nice values on our unit circle, right? We'll do more of these so that you get a little more practice with them. But I think that's good enough time. Y'all good? Try the homework, okay? Let me just double check that it's doable at this point. Trig equations. Yeah, it's going to be interesting to see how you do on this.
Are you going to be putting homework videos up?
Pardon?
Are you going to be putting homework videos up?
I know I've been terrible. Can I start with these? Because I feel like I can't make up the ground that I've lost. I'm going out of town this weekend, so and starting actually right after class, I'm going out of town. So the videos would have to be done on Monday, so I wouldn't have them up until Monday. Yeah. Okay, today's what, the 19th? Okay, I'm going to pass this around. This is the sign-in sheet. Go ahead and try all the homework, see how it goes. I anticipate there will be some questions. Now, for those of you who came into class not late, well, no, I guess you were late if you didn't get your test.